Massachusetts, and he will speak about graphical representation and clustering.
Thank you. Well, I'd like to thank the workshop organizers and Alan Sokol for inviting me here. So we're going to descend further into the purgatory of physics, and you're going to see actual numerical results, but nothing will be proved. Okay, so I'm going to pick up where Alan left off and give you a discussion of the Swenson-Wang algorithm and the underlying graphical representations that presumably make it work so well. And then the goal generally will be to see if we can extend that very beautiful idea to some other situations where the original Swenson-Wang idea doesn't apply. And the first of those will be the random cluster model that Alan mentioned for cases that Q is not an integer. And then we'll talk about what to do if there are, say, external fields or frustration. And actually in those last cases, except for in some special circumstances, there really isn't much that can be done. And we'll see how far into that second topic we can go. Okay, so graphical representations are, first of all, tools for rigorous results on spin systems. And then, from my point of view, the most interesting thing, the basis for very efficient Monte Carlo algorithms of the kind first introduced by Swenson and Wang. Actually, maybe one should also include an algorithm that Sweeney introduced for the random cluster model even before then. And finally, it's a source of some geometrical insights into phase transitions. And so you'll be able to tell that I'm an American physicist because not only will I mispronounce Fortune and Castellan, but I'll also mispronounce Ising hereafter. So the history goes back to the 70s, and the mathematical community was rediscovered in the early 80s by Cornelio and Klein in the physics community, and then built into this beautiful algorithm by Swenson and Wang. And then I think the nice picture that Alan was too shy to mention that he was really the one who introduced of having a joint distribution was due to Edwards and Sokol. So this is the Edwards and Sokol joint spin bond distribution that written in rather different notation, but the same idea that Alan ended with, that we can imagine. So we have now a lattice. I'm always going to be talking about lattices, except for a few comments about the complete graph. We have some spin variables, so these are the arrows, and we have some bond variables or edge variables, and we have a joint distribution, and so I'm going to just call it a statistical weight. It's not normalized here. It has, first of all, just a sort of Bernoulli percolation factor in front, p to the number of occupied bonds. So I'm going to call such a thing where an omega is a 1, an occupied bond, and 1 minus p to the number of unoccupied bonds. And then the only other thing that's in this distribution is a constraint, which says that I'm only allowed to occupy satisfied bonds, and satisfied means the two Ising spins are pointed in the same way, either both up or both down. So that's the joint distribution, and this constraint just says every occupied bond is satisfied. Okay, so the nice thing about this Edwards-Sokol joint distribution is that its marginals are the Fortune-Castellan random cluster model. That is, if you integrate out the spins, it's obvious that so each component of the graph of occupied bonds can take exactly 2 spin values, because throughout the component the spins are the same, so it's 2 to the number of components, and then nothing happens when you integrate out the spins, so you get exactly this random cluster model in the particular case here of Q equals 2, but you could do the same thing for any Q. And C of omega is the number of components, or I'll typically call them clusters. It's a little bit less obvious, but only a couple of lines of work, and Alan sort of did that on the board to see that if you integrate out the bond variables and choose the particular value p equals 1 minus e to the minus 2 beta j, you get the Ising model. Okay, so let me just now go through how the Swenson-Wang algorithm works pictorially. Okay, so we start with the spin configuration. We occupy bonds, satisfied bonds only with this probability. So I've done that with the red bonds. Then we identify clusters of occupied bonds, and then we erase the old spins and repopulate the lattice with new spins, satisfying the constraint that in each cluster or each component, the spin configuration is the same direction. Or another way of saying it is randomly flip each cluster with probability 1/2. So that's the Swenson-Wang algorithm. And why does it work well? Well, nobody really knows, but you can at least get some understanding because of a connection between basically all the information in the bonds, and the spins and the bonds contain the same information, and the bonds contain the information in a kind of a nicer geometric way. That is, the spin correlation function, the correlations between spins at I and j, is actually just the probability that I and j is connected in one of the clusters. And what that means is that broken symmetry, the phase transition is marked by the onset of a giant cluster. Right at the phase transition, there are clusters of all sizes, and so in one move of Swenson-Wang, you're basically modifying the system on all length scales. So that's presumably why it works so well. So we can now talk about making use of the finite size scaling that Alan introduced, and talking about a time scale which we'll here say is an autocorrelation time of, say, some observable like the energy. And that time scale diverges with the linear dimension of the system with to a power. So this is all at the critical point, and all the rest of this discussion is going to be concerned with critical points. So there the time scale diverges as some power of the linear size of the system, and that's what we'll call the dynamic exponent. And very little is known about this dynamic exponent except for a lower bound which Alan and Lee proved, and that is that z is greater than or equal to these two other equilibrium exponents, the specific heat exponent divided by the correlation length exponent. And luckily in most systems, that ratio alpha over nu is quite small, which at least allows Swenson-Wang to work very efficiently. Okay, so now we'd like to think about ways that we can, so this is a beautiful idea. It revolutionized numerical or computational statistical physics. No one would think of using Metropolis now at the critical point for a system for which you know how to do some kind of cluster algorithm. And now we'd like to think, are there ways to go beyond the Potts model, which was the original domain in which Swenson-Wang introduced their algorithm. And then shortly thereafter, Wolf introduced an algorithm that allows you to generalize to the kind of model we heard about this morning with continuous symmetries rather than a discrete symmetry like the Potts model. So here is one direction that we can generalize, and that's to the random cluster model itself for non-integer Q. And actually there are two goals. One is, can we have an effective means of simulating this model? And the other is to try to understand some things about the Swenson-Wang scheme more in a larger range of settings than we had before, so that we can see, for example, one question is this Lee-Sokol bound sharp or nearly sharp? Well, we only have a few examples for integer Q available that don't have first-order transitions, where we don't expect things to work very well. So we'd like now, if we could figure out how to generalize the Swenson-Wang idea beyond integer Q, we could see see how it works. So what do we know if for Q not too large and D greater than 1, there's a continuous phase transition, or this is no in the physicist sense. Above a critical Q, the transition is first order. Q equals 1 is just ordinary percolation. Q equals 2 is the Ising model, and so forth. So anyway, how can we generalize this idea of having some kind of joint distribution of spins and bonds, which we can simulate by the Swenson-Wang idea? Clearly, if we've got 1.5, if Q is 1.5, we can't have 1.5 types of spins, but maybe we can have one type of spin that represents one of those 1.5 components, and then the rest will be left to their own devices. So here is a joint distribution which is has some spins that take values 0 and 1. The ones I'll count as blue. It has some bonds, and it has sort of part of the Q to the number of components of the underlying random cluster model, but not all. It has Q minus 1, and the number of components is the number of inactive sites. And so what do I mean by inactive? I mean the sites that are not painted blue. So in this particular picture, the number of inactive components is 1, 2, and then there's those singletons. I think there are 5 of them. Okay, same Bernoulli factor, same constraint that every occupied bond is satisfied. And the nice thing about this joint distribution is if you integrate out the spins, you'll get the random cluster model. And that's an easy thing to see. It's just kind of a binomial sum over those Q minus 1 C to the sigma omega. So again, the bond marginal is a random cluster model, but now we have this option of going back and forth between modifying the spins, these blue dots, and modifying the bonds. But we're only going to modify the bonds where we know what the spins are actually doing. That is, we're going to erase all the bonds between these blue dots and then repopulate them. And so we're doing sort of part of the Swenson-Wang move only on the spins that we know about. Okay, so here is the algorithm for the random cluster model. We start with a configuration of bonds. So the red places are where omega is 1. We declare active fraction 1 over Q of the components or clusters. So say this component is declared active, this one is, but this one isn't, and so forth, and with the probability 1 over Q. And this is the actual conditional probability given the bond configuration omega of coming up with a spin configuration sigma. Then we're going to erase the active bonds and repopulate the, that is the bonds that are connecting blue dots, and repopulate them again according to just Bernoulli percolation. But only, we're not going to do any, not allowed to do anything around here. We can only say do things here. Yeah?
Is the pointer there somewhere?
Oh, pointer. Yeah, that's better. Okay, thank you. Well, quite get the silver button on the top. There we go. All right. Okay, so there's the last step. I've now repopulated the active bonds. Okay, so now here's some actual numbers. How well does this work? So this is work done with Alan, and I particularly want to mention Tim Garoni, who did the lion's share of the numerical work, and there's a lot of CPU years here, actually. And so what you should look at is here is a whole range of Q from from 1 to 4. We don't go above 4 because that's where the system goes first order. And here is the dynamic exponent extracted by this finite size scaling. So we look at a range of system sizes, look at the autocorrelation function of an energy-like quantity, and then look at the integral of that autocorrelation function. So that's the integrated autocorrelation time, and then see how that grows with system size. And then this is for the two-dimensional random cluster model and for system sizes up to 1024. And then you have to be careful not to use too small systems to do the fitting, or you won't get something that's close to a power law. But what you see here is that the dynamic exponent, and remember for, say, Metropolis, dynamic exponent is always going to be roughly 2, except, in the trivial case of percolation. Here it's very tiny. Even for Ising, it's 0.14, until you start getting close to the first order transition where it approaches 1. And the other thing you see is it seems unlikely these numbers, while small and having the same trend as alpha over nu, are not the same as alpha over nu. So probably the Lee-Sokol bound is not a sharp bound. And I should comment, this is not a violation of a mathematical theorem, but the fact that when you're right at q equals 4, there are logarithmic corrections that make a fit like this probably inappropriate. Okay, so for the three-dimensional random cluster model, nobody knows where the transition to a first order transition is in Q, but it's somewhere not far above 2.2. And again, we see that for Q, for the sort of below the Ising situation, Z is very small, and that's a range where alpha over nu is actually negative, so it doesn't tell you anything. And then and right at the Ising case, it's about, Z is about a half, and then it grows. And again, the Lee-Sokol bound is apparently not a sharp bound, so it's still an outstanding question. What is it? What is the slow mode of the Swenson-Wang type of algorithm? Okay, maybe I should take questions here before I move on to the second topic. Yes? Alpha in 2 dimensions is known exactly. It's not, I think, rigorous, but it's exactly known. In 3 dimensions, it's just, no. It's renormalization group or numerics. Oh, actually, I should, okay, so there's one more case, and that is if we look at the mean field situation or the complete graph, then in fact, we know, not rigorously, but from heuristics, that Z is 0 in the range Q goes from 1 to 2. And this, I just learned, is rigorously known for Q equals 2. For the Ising case, then Z is 1. And for Q bigger than 2, there's a first order transition, so presumably there's exponential slowing. And you can non-rigorously obtain this by looking at the dynamics under this random cluster Swenson-Wang kind of move of the size of the largest cluster. And you can see that Q equals 2 is a special situation where you have this dynamics leads to a power law decay, whereas for Q less than 2, you have exponential relaxation. Okay, so the conclusions of this first part are that the Swenson-Wang scheme can be extended to non-integer Q random cluster models, and apparently the Lee-Sokol bound is not sharp. Okay, so we're going to descend further into physics purgatory and think of some Ising systems that are nastier. And so I think I'm only going to be able to talk in any detail about the first one, which is the least nasty of them, the Ising model in a staggered field, but maybe we'll have time to talk about the spin glass and certainly not the random field problem. So what is this? Well, the J's are just going to be 1, so it's a ferromagnetic Ising model. but we're going to go on, say, the square lattice, so a bipartite lattice, and the H's are going to alternate. So on the red squares of the checkerboard, the field will be up, and on the black squares be down. And so there's sort of a competition. If the field wins, so if the H term wins, all the spins will want to be just staggered. And if the J term wins, then they'll like to be ordered. And so what is known is that if you don't make H too big, actually the right quantity to look at is H times temperature. Anyway, if you don't make that too big, then you can have a continuous phase transition, which is in the Ising universality class. If you make it too big, then this term just always wins. So we'd like to see, is there a way of simulating, say, this critical point or this critical point? So this is a whole line of critical points separating a high temperature disordered phase from a low temperature ordered phase. Okay, this is the spin glass. I think we'll come back to that later. So the Swenson-Wang algorithm, you could use it if you wanted to, but you'd have to do something. So you generate clusters as before, but now you'd have to say what is the energy of the field on each of those clusters, and you'd have an acceptance fraction for whether or not you're actually going to flip the cluster. And so the big clusters are going to be frozen. So that's one problem. Another problem is that nice relation that we saw between spin correlations and connectivity, that's lost. And so in fact what happens is way out in the high temperature phase there's already a giant cluster. And so actually Swenson-Wang is, for this model, as soon as you turn the field on to any significant degree, is far worse than Metropolis. It's just kind of frozen and bad. So is there anything that we could do to use a kind of a Swenson-Wang idea? And it turns out there is, and it's slightly Baroque. It involves two replicas of the spin system rather than one. And these two replicas are entirely independent. So you can look at one and collect statistics or look at the other, whatever you want. But we need two replicas in order to grow our bonds, to have the bond or the graphical representation that's going to go with the spin system. So we've got two sets of spins, the green ones and the brown ones, or sigmas and taus, and we're actually also going to need two types of bonds now. So blue ones that are omegas and red ones that are etas. And here are some relevant papers. The first two are actually the first one, a form of this idea was introduced by Swenson and Wang in the other Swenson-Wang paper from that period, and they had applied some variant of this idea to spin glasses, and we kind of rediscovered it and enhanced it, and then these last two papers I probably won't be able to talk about have to do with applying it to spin glasses. Okay, so there is, again, a joint distribution of spins and bonds, and it's rather nasty looking, but it has the features of Bernoulli factors for both kinds of bonds and some constraints that are actually very simple. So let's not worry about looking at the mathematical description of the constraints, but let me just state what they are in pictures. So the blue bond must be put down only where both replicas are satisfied. So the green spins are aligned and the brown spins are aligned. So that's where I'm allowed to put a blue bond. They don't need to be aligned with each other. They're independent of each other, but so this is okay here too for a blue bond. All the greens are aligned and the browns are aligned. The red bonds are allowed wherever one replica is satisfied, the browns here, and one is not satisfied, exactly that situation. And they also go with different probabilities. This is that old probability that we saw for Swenson-Wang. This is a higher probability, 1 minus e to the minus 4 beta rather than 2 beta. Okay, what are the properties of this Edwards-Sokal kind of joint distribution of two spins and two kinds of bonds? Well, again, if I integrate out the bonds, I get the Ising model, two independent Ising models. Now there's no fields here, and we still have to worry about the fields. Also, if I look at not the usual magnetization correlations, but the correlations of what's known as the Edwards-Anderson order parameter, which is another way of seeing order and in fact the right way to see order when there are either fields or frustration present, then again I have a relationship to connectivity, but it's a little bit more complicated. So this correlation of this kind of order is equal to the probability of connectivity by a path with an even number of those red bonds minus the probability of connectivity by a path with an odd number of the red bonds. And it's obvious why you have this minus term here, and that's because whenever you go down a red bond, you actually switch one of the spins in one of the replicas, and so this quantity flips sign. Okay, so some more properties. For a purely ferromagnetic model like the Ising model in a staggered field, you can show that percolation of those blue bonds, the ones that connect satisfied things at both ends, is equivalent to broken symmetry. So there's still now a nice signature of the phase transition geometrically. Once you introduce antiferromagnetic bonds, then things get more complicated, and I think I'm not going to have time to talk about that situation. So there is now an algorithm that goes with this two-replica graphical representation, and again, it's a little bit more Baroque than Swenson-Wang, but it's easy to see the pictures. So given two spin configurations, two totally independent spin configurations, but in the same, if the staggered field is, say, up here, down here, up here, both of these spin configurations feel that same staggered field. So given the spin configuration, I now lay down the bonds with these two probabilities, of which part of them have been chopped off. I identify clusters, and then I basically repopulate the spins anyway consistent with those constraints. So, for example, if I started here, I can produce a spin configuration for this cluster like this. So in this case, I flipped both replicas, but I could flip one replica or, and for example, here, so I only flipped one of the replicas, and then I needed to flip something here too so that I maintained the constraint of this red bond. So again, a little more complicated, but the same idea as Swenson-Wang. And a nice feature of it is, even though I still have field energies to worry about from the staggered field, for certain kinds of flips, there's no field energy because the net field energy change of going from here to here is 0. And that's a key ingredient of this, this new algorithm. So here it is all again in words, so I won't read through the words, but I do want to say that to actually make this work, you need some add-ons. And the particular add-on you need that's an allowed move in a staggered field is to translate one of the replicas relative to the other. If it's an even translation, you just translate it. If it's an odd translation, you also have to flip it. And those are legal moves. If you want, you can also throw in metropolis sweeps. And if we're talking about something like a spin glass, you might want to throw in something like parallel tempering. So how well does this work? So here is the two-dimensional Ising model on a square lattice in a staggered field. And now this is looking only at a particular size, L equals 80, so that's not actually very big, but looking at 3 different strengths of the field. And again, we're right on the critical point. And first of all, let's look and see. So Swenson-Wang does really well when the field is 0. So its autocorrelation time for, in this case, the magnetization is 4. But as soon as you turn the field on, it's a disaster. It goes from 4 to 4,000 and 5,000. Metropolis is always bad and gets worse as you turn the field on. This algorithm, well, for h equals 0, it's not as good as Swenson-Wang, but it doesn't get any worse. It doesn't really care that you turned the field on. We don't have good enough data to say we know what the dynamic exponent is for this algorithm, But we do have enough data to say that for 2 dimensions, it's less than a half or so. And a conjecture is that it's as efficient as Swenson-Wang, but that we don't know. Okay, so I think I am out of time. Let me just, how much time do I have?
0.
0, okay. All right, so in that case, I'm going to conclude and not talk about spin glasses and just leave you with the lesson. There are ways to go beyond the original Swenson-Wang idea and still apply cluster algorithms, and lots to be done either to show in a rigorous way how well they work, or also to try to devise new domains where they will work.
Questions or comments?
I have a small comment, which is that Professor Ising was once asked how he pronounced his name, and he said that when he spoke to German audiences, he said his name was Ernst Ising.
Mm-hmm.
And when he spoke to international audiences, he said his name was Ernst Ising.
Aha.
So you're actually...
I'm actually correct.
Actually, I also have a question about names. You listed some references, and
Yeah.
there were 2 papers involving a Newman.
Yes.
Are they both Chuck Newman? But they
Actually, there's also a Mark Newman in there.
Oh, okay.
Yeah.
Okay, so that answers my question. Other questions or remarks? Then.
Physicist Mark Newman, who now does sort of social networks.
Yes. Yes.
Okay, let's thank John again.